Thursday, so that will cover this theorem up to this. Actually, I posted a reading list, but on this module, the topics for the assignment, which is a quiz, is going to be from the posted the slide numbers. So it's going to be all on this definitions and the relation between the different classes of problems and this polynomial reduction and so on, and all these kind of theoretical topics, as well as on this theorem that we just went through the proof. Okay, so make sure you go through the reading list. So you could prepare for the reading with the reading list, and I'll post the quiz quite soon in this weekend. You can take the quiz only once, so it means you should be prepared on the topics really. But of course, while taking the quiz, you could refer to the notes because it's open notes and do the quiz. And it's a timed quiz, so it will be for a certain time, like 15 or 20 minutes or so on, like that. So you should finish within that time, and you can take the quiz only once. So that's why I posted the reading list so that you can start preparing on those topics, and I'll post the quiz quite soon in Canvas. Okay, so that is the traveling salesman problem, and we went through 2 heuristics for that. Now let us focus on 3 kind of what you call kind of data structures, but 3 entities, as it is, you can call like that, called independent set, Vertex, cover, and Clique, and they are all related to each other. And we are going to get several things out of these 3. We are going to see how we can use one single algorithm, okay, one single heuristic, and actually find all these 3. So that is something we have not seen so far. So, and that means we are also going to see how a problem can be, for finding one of this, can be reduced to a problem to find the other. That is this polynomial reduction that we went through earlier between Hamiltonian circuit and traveling salesman problem. And we are going to apply the polynomial reduction here also to see how we can determine one of these 3 using a heuristic to determine something else. Right? Okay, so let us first see the definitions of these 3 things, and then we will look at the heuristics. I don't know why it's coming out. Okay, so what is an independent set? So in a given graph, an independent set is the set of vertices. For example, for this graph, I can say V2, V4, V6 is an independent set such that there is no edge between vertices in the same set. So you see here, there's no edge between V2, V4 in this given graph. There's no edge between V2, V6 in this given graph. There's no edge between V4, V6 in the given graph. So this is the set of vertices such that there's no edge between vertices in the same set. So we call such a set of vertices as the independent set. Okay. Now again, obviously, then we would be interested to find what is the largest possible independent set for a given graph, because even an empty set can be called an independent set because there's no edge between any 2 vertices in that empty set. So and again, I can say V2 by itself is an independent set because there's no edge between 2 vertices in that set. V2, V4 is also an independent set because there's no edge between V2 and V4. So can we add V6? In this case, yes, V2, V4, V6 can form an independent set because there's no edge between any 2 vertices in that set. Can we add one more vertex, say V1? If I add V1 to this set, V1, V2, V4, V6, they cannot be called an independent set because there's an edge from V1 between V1, V2 or between V1, V4. So in order to be called an independent set, there should not be an edge between any 2 vertices in that set. So obviously we are interested in finding what's called the maximal independent set. What is the largest possible subset of vertices such that there is no edge between any 2 vertices within that subset. So that is the, so an independent set problem will focus on is the maximal independent set problem. Okay. Now again, it could have a lot of applications. So if you have a social network of people, what is the largest grouping of people such that we don't no two people in that grouping know each other? That's like a good practical problem for finding a maximal independent set. Now, the second thing called vertex cover is defined like this. So a vertex cover is again a subset of vertices such that for any edge in the graph, at least one of the two end vertices will be part of the vertex cover. So that's the definition. So let's apply the definition again. So vertex cover means, so I've given the definitions in the previous slide actually. So a vertex cover is a subset of vertices such that for every edge in the graph, at least one of its two end vertices. So at least one of the two end vertices should be in the vertex cover. So let us check. For V1, V2, V1 is in the vertex cover. For V2, V3, V3 is in the vertex cover. For V1, V4, V1 is in the vertex cover. For V2, V5, V5 is in the vertex cover. For V3, V5, both V3 and V5 is in the vertex cover. So that's fine. I said at least one of the two end vertices should be in the vertex cover. So in this case, both end vertices are there. That's fine. So again, the entire graph, the entire set of vertices, all the 6 vertices could be considered as a vertex cover, because if I say all the 6 vertices form the vertex cover, then it automatically satisfies the definition of a vertex cover. For every edge, at least one of the two end vertices will be in the vertex cover. So that means we are not interested in finding the largest possible vertex cover, we are interested in finding the smallest possible vertex cover. Okay, so that's the notion behind vertex cover. So for a given graph, we are interested in finding what is the minimum vertex cover. Okay, such that for every edge in the graph, at least one of the two end vertices are in the vertex cover. Now you may be wondering, these two are independent problems. Finding an independent set and finding a vertex cover are two independent problems. So actually find the maximal independent set and find the minimum vertex cover are two independent problems. But no, they're really one problem. So let us again go back to the definitions. So when I said independent set, I said there should not be an edge between any two vertices in the independent set. That means, go back to an edge here. So for any edge, we cannot have both its end vertices to be listed in the independent set, right? So for edge say V1, V2, I can't have both V1, V2 in the independent set, right? So that means at least one of the two end vertices of an edge should not be in the independent set. So it should be in a set which is called the complement of the independent set, right? So at least one of the two end vertices should be out of this independent set. Out of the independent set means what? It should be located in the complement set of an independent set. So from set theory, from your digital or discrete structures class, you would have known what's the complement of an independent set of a set. So you would have known there that given a set of vertices, the complement is simply the vertices other than the one that is in this set. So V2, V4, V6 are in this independent set. So what is its complement? V1, V3, V5, which are not in this set. And you notice V1, V3, V5 actually form the vertex cover for this graph. Okay, so that means for every edge, at least one of the two end vertices should not be in the independent set, should be in where? Should be in the complement of the independent set. That means should be in the vertex cover. And think about it, if you call this as a maximal independent set, so the set of all vertices minus the maximal independent set will equal the minimum size of the complement. So that's why it's a minimum vertex cover. So you have 6 vertices. So if I try to increase my size of the independent set as large as possible, say to 4 or 5, depends on the graph again. So 6 minus say 4 will be equal to 2, whereas 6 minus say 2 will be equal to 4. So that means if I do 6 minus a larger value, which is the maximal independent set size, I'll get a minimum size for the vertex cover. So that is why. And what is the vertex cover? What is the minimum vertex cover? It is simply the complement of the maximal independent set, or anything, even even if it's not maximum minimum. Once you find the independent set, we can say the complement of it is the vertex cover. Okay, and it's applicable for maximal independent set and minimum vertex cover. So that is why, if you once you find using a heuristic the maximal independent set, the complement of that independent set is going to be the minimum vertex cover. So using one heuristic, by running it once, you can find both of them, and that's what we're going to do after we look at the definitions. Okay, so this is a reduction, this polynomial reduction. Why? Because all we need to do is find a complement. So once we know the set of all vertices and we know the independent set, just remove the vertices from that all the vertices universal set, this vertices that form the independent set, and what we get is a complement. So this can be done in polynomial time. So once we find the independent set, we can find the vertex cover in polynomial time. That's a polynomial reduction. Now what is the third thing? The third thing is called the clique. Now a clique by definition is like you have a subset of vertices such that you have an edge between any two vertices in that set. So in this graph I can say v1, v2, v5 is a clique of size 3, right, because there are 3 vertices in this clique. Now can an edge be called a clique? Yes. I can say v1, v2 is a clique because between any two vertices in that set there's an edge between them in the graph. So v1, v2 or v2, v5 or v1, v5, any edge, the two end vertices that are part of the edge can be said to form a clique. Okay, so that means we are interested in finding actually what is the maximum size clique, because we can find obviously clique of size 2, each edge is a clique of size 2, and each triangle is a clique of size 3. So what we are interested in finding is what is the maximum size clique in a given graph. Okay, and by going through an example, I'm going to show that the heuristic that we use to find the maximal independent set can also be used to find the maximum size clique, and that's the kind of polynomial reduction there. Okay, so we'll show that using an example. Alright, so let me stop this video and then save it. I'll come back.